Hey coders, today we're going to build solutions in both Scratch and in Python for the third Project Euler problem. We'll be making some connections between the visual coding blocks in Scratch to the less visual coding functions and tools in Python. I'm not doing a whole lot of explicit teaching you about each and every block. I'm hoping that you have some familiarity with both languages, both Scratch and Python, but then as we apply and use and create using these tools, you'll get to know the tools better and see some of the connections between the languages. So the third Project Euler problem gets us into prime numbers. Let's take a look at the problem. Okay, the website is projecteuler.net, and this is problem 3, largest prime factor. So it just says the prime factors of 13,195 are 5, 7, 13, and 29. And then our question that we're going to solve today, what is the largest prime factor of the number? And then I'm not going to try to read that number. It's a huge number. But our task is to find the largest prime factor of that number. And to get started today, we're going to work on paper pencil. We're going to start with paper pencil. Okay, the basic definition of prime numbers. A prime number is a number that has exactly two factors, 1 and the number itself. My two young children got way into number blocks, this British public television show where they represent the numbers as characters that are built with these types of blocks. So there's the number 1, the number 2, the number 3, and they would often have the number 4 walking around as this square character. And just here's also one of the ways that the number 6 would often form up. So in number blocks, and I like this as a very visual way to think about the definition of primes. The definition was a number block is prime, or a number is prime, if it can only ride 2 tracks. And what it meant by this is a track would be like space this wide, so this number 2 here could ride on the one track, or it could ride on this track, and that would be called the 2 track. Now, this 3 also could ride on the one track or the 3 track, but when we get to 4, it could ride on the 2 track, just like 2 sliding horizontally here could ride on the 2 track. The 4 could also ride on the 2 track, but the 4 could switch its form and then also be able to ride on the 1 track or the 4 track. So the 4 can actually ride on 3 different tracks. And all of this is just another way of talking about factors. If the number of blocks can be formed into an even rectangle, that shows us the factors. So here's 6 and 2 and 3, the sides of that rectangle, are 2 of its factors. 1 and 6 are other factors. So a visual way to think about prime numbers is they can only ride 2 tracks when they're formed into even rectangles. So just to continue a bit with our review and understanding of prime numbers, let's gather up and think about the first several primes. So 1 is not prime. My kindergartner will correct you if you try to say it's prime, because 1 cannot ride 2 tracks. It can only ride 1 track. It only has 1 factor. 2 is the first prime, and it's the only even prime, because all of the numbers that are even, that are greater than 2, can be divided by 2, and that means they can ride the 2 track. So 4, 6, 8, 10, and 12 we can cross off because they are all even and can be divided evenly by 2. 3 is the next prime. 5 can't be divided by anything evenly except 1 in itself. Same with 7. Now 3 is odd, so it didn't get crossed off yet, but 3 times 3 is 9, so 3 is not prime. And 11 can only be divided by 1 and 11, and 13 can only be divided by 1 and 13. So those are the first 6 prime numbers. And another concept we're going to need to understand for this Euler problem is prime factorization. Every number has a unique prime factorization. And when I was in about 6th grade, we would learn how to find the prime factorization by following a process like this. I take a number that I'm starting with, so I'm finding the prime factorization of 500, and I think of two numbers that multiply to be up the corner of the top of this branch. And then once I hit a prime number, that branch is done. But 100 is not prime. 10 times 10 is 100. And 5 times 2 is 10, and 5 times 2 is 10. So I can represent now the prime factorization of 500 as the product of all of the end of all of these branches. So there's two 2's, so 2 to the second power, and there's 3 5's. And one of the interesting fun things to do with this technique is you can start with different numbers. So 25 times 20 is also 500. 25 is 5 times 5. So now this branch is done. And if we go all the way down, we're going to see that even though I got there with different branches, I still have two 2's and 5 3's. So no matter how I decide to go down my branching, I'm going to end up with the same prime factorization. And if I multiply 2 times 2 times 5 times 5 times 5, I would get back to 500. This is the prime factorization of 500. So that's just some starting out review of prime numbers and prime factorizations. Okay, so our Euler problem is asking us to find the largest prime factor of a very big number. And to do that, we are going to find the prime factorization of that very big number. And there's an algorithm that we can use to find the prime factorization using a sieve. And the reason we're going to do it this way is because it's not going to require us to find out or to do some sort of check to see if numbers are prime or not. It's going to get the prime factorization without even ever having to know in the code which numbers are prime. So here's how the sieve is going to work. We'll start with 500 again. And we're going to start out with 2. Every time we run this algorithm, we're going to first check and see if the number is divisible by 2. And if it is, we're going to divide the number by 2. And then the numbers over here on the left, we're going to collect in a list, and this will be the prime factorization. And then this number over here on the right, every time we divide, I'm going to call it the shrinking number because it's going to get smaller and smaller. So first step is to divide by 2, and then we do that step again. We'll write some loops, and as long as we can, we'll keep on dividing by 2. So we are collecting the primes over here and our shrinking number over here. And once we can't divide by 2 anymore, we go to the next number. So in 500, I ended up dividing by 2 twice. So then we check and see if 125 is divisible by 3. And it's not. And then here's where the sieve starts to come into play. I'll just put a line here. There was no 3's that we could factor out. Even though the number 500 is divisible by 4, 4 can evenly divide into 500. It cannot evenly divide into 125. And the reason is because I have already divided 500 by 2 times. 2 times 2 is 4, and I already divided 4 out of the number. So by the time I get to 4, then my number isn't divisible by 4 because I've already divided the number by 2 as many times as I can. And that's going to be true of any number that's um, just made from 2's. So for example, if 8 is divisible into a number and I'm following this algorithm, when I get to 8, it won't be divisible by 8. And similarly, in this problem, I already divided by 2 and I already tried to divide by 3, so 6 isn't going to be a factor of the origin of the shrinking number. So even if it was a factor of the original number, it won't be a factor of the shrinking number by the time I get there. And so following that algorithm, I will check and see if 4 can divide into 125 because I'm not going to do any code that tells my program which numbers to skip. We're just going to go in order. But because of the order that I'm doing this, I know that when I get to my shrinking number, a composite number, that means a number that's not prime, won't be able to evenly divide into the shrinking number. Only prime numbers will. So 5 will be able to divide into this number. Oops, just 25 there. And 5 will be able to divide into it again. So we had 2 5s, and then 5 can actually divide it again. We could do 5 divided by 5 is 1, and that's how we know that we're done, is when our shrinking number equals 1. So that's a example and explanation of how a sieve works as an algorithm, and this is what we're going to code in both Scratch and Python. All right, let's get started. I have put 2 sticky notes up here and outlined my plan, just following those same steps that we just did with paper marker. And the first thing I'm going to do is get an event when the green flag is clicked and start making my variables. So we're going to need a variable that I'm just going to call number, and that's both our starting number and that shrinking number. And when we initialize it, let's put it to 60. It's a good one to run some tests and see if our code works. So it'll start out at 60 number. Let's delete this one so that I don't get confused. All right, so when we start out, our number will be 60. And then when we're all the way done coding, we'll put in that big number off of the Euler website. The other variable that we'll need to start we'll call divisor. So that's what we'll start out as 2, and then go up 1 at a time, just increment up by 1 as we're running our solution. And it will be the number that we'll only ever get onto our list if it's prime because of that sieve. And then we also need a list. So let's make a list and we'll call it prime factors. And we'll move it over here, prime factors. And I think, let's make sure that we can set that list back to 0, delete all of prime factors when we restart our program. So we have our 2 variables and our list where we'll collect the prime factors. And now let's do another event when we start the program. And for this one, we'll start building our algorithm. So what we're going to need is a control block with an if in it. And what we're going to check very first, just thinking about this 60, is if 60 is divisible by 2, then we want to divide it by 2 and change the number to the result of dividing by 2. So to do the if 60 is divisible by 2, we'll use the mod block. So if the number mod the divisor equals 0, then that means it is divisible by 2. Then we're going to add 2 to our prime factors list. So that's one thing that we'll do if this is true. Add the divisor, which in our thinking through with 60, that means we'll add 2 to the prime factors list. And we're going to change the number. So we'll set the number to the answer to that division problem. So that this is where we're shrinking the number. So we'll set the number to, number divided by, maybe if I build it out here, divided by divisor. So let's just run this through one time and see what happens. 2 is a divisor, and so it goes onto our prime factors list, and we shrink down to 30. And we just want to run that again and again, so we're going to need a repeating block. Let's see. Let's grab a repeating block, and eventually we'll be getting a condition that we can stop when the shrinking number is 1. But for now, we'll just leave that there. And I just realized we actually need an if-else to make this work, because if this isn't true, we're going to need to do something else. So let's just pull the if-else and build it by pulling this apart. Okay, so now we didn't actually need the plain if block. We need if else, because if this condition, if the number, which as we're repeating this loop becomes the shrinking number, is not divisible by the divisor, then we need to go to the next number. We need to change that divisor by 1. And there's a block right here that does exactly that. So now let's think about the repeat until. How many times or when will we know we're done? Well, we'll know we're done when the shrinking number is equal to 1. And that should add all of those prime factors onto our list. So let's try it, see if it runs with 60 now. When I reset it, it'll go back to 60, but then it'll immediately run the code. So 2 times 2 is 4, 4 times 3 is 12, 12 times 5 is 60. I think we've got it. Let's try it with a couple other numbers that we can think through the prime factorization. So if we set it to 100, 2 times 2 times 5 times 5, yep, that's the prime factorization of 100. So this loop here with if-else block in it, where we're following that algorithm that we wrote out with the paper, is working. And the only thing we'll still add to this code to solve the Euler problem is something that will pull that last number or the highest prime factor off the list. And the way we're going to do that, we'll have Scratch, the cat, say the answer, is get one of these join blocks. And what we need to think about is how to represent the last number on the list. He'll say space is the largest prime factor. And we'll get back into these items. So we're going to have an item of the prime factors, and what we need to put in here is which item. Well, we want the biggest index numbers item, and we're going to get that by doing the length of the prime factors list. So the length of the list will be the highest number on the list. So let's see if this works with, what do we have in there now, 100? So it should say, Scratch should say the largest prime factor is 5. Let's try it with another number. Let's see, maybe, what's 17 times 5? 85? Make sure he says 17. Yep. So our code's working, so let's grab that big Euler number and paste it in here, and then we will have the solution. So here I'm just off screen grabbing that number for us, and will Scratch online be able to get the prime factorization of that very big number? Yes. Our code worked, and there is the prime factorization of our super big number. And here is Scratch saying the largest number. I guess we could have just pulled it off the end of the list, but either way, here it is, the solution to the third Project Euler problem in Scratch. And now we're going to jump over and do it again in Python. Okay, now the same solution following very similar process in Python. And I'm on the website replit.com. You can get a free account, get right into coding in Python with very, very little setup or installing hassles. So here we are in Replit. And just like in the Scratch solution, I'm going to start with a few variables. So we'll have our starting number, and we'll start with 60 again. We need the divisor, and we'll start with 2 again. And we also need a list, and it's again going to be called prime factors. But in Python, it has to be that one word with the underscore. So there's our empty list. And now the loop that we had in Scratch that said repeat until. The way we write that same function in Python is we say while, and then we write a condition. So while the number is greater than 1, we're going to do our if and our else. So if I jump back over into my code in Scratch, we're in this part now of coding the same solution in Python. And this would be a great place to stop and finish your code in Python, or you can just keep on watching and coding along with me. So while our number is greater than 1, we need to first check and see if the number is divisible by that divisor. So if number mod divisor is equal to 0, so that's a Boolean, so we need that double equal sign. Then, oh, I forgot my semicolon. let's see, getting the tabs right is important in Python. So if it is divisible by 0, then we'll set the number equal, and I'm going to put this int in here to make sure that it stays an integer and doesn't change to a floating point number. And we'll also append, that means add to a list. So we'll append onto the prime factors list the divisor. And then if it's not divisible, then our else is we'll add 1 to the divisor. Divisor add 1. And so we've coded that same loop that we had in Scratch. And just to test it, let's have it now print the list of prime factors. Okay, and run the code to test it. So it printed 2235, which is the prime factorization of 60. So we've replicated our Scratch code now in Python, except for that final printing the last number on the list. So let's use an F string to do that. And we'll say the largest prime factor is, and then we'll need to do a similar variable here as we used in Scratch, and we'll want to have the length of prime factors as the index. So we'll use this, and we'll actually need to do -1 because indexing in Python starts with 0. So we have a 1 off here, and then we just put the name of the list. So let me slide this and make sure you can see that whole thing. So if this is working correctly, then when we do the prime factor, or when we start with 85, we should get 17. An end of line. Oh, that means I forgot my final quotation mark because see, it said my end of line error code, which is one of my most common errors. Okay, we just needed that quote right there. The largest prime factor is 17. So now we'll grab that number from the Euler problem again, put it in for our starting number, run the code, and we have the same answer as we had in Scratch. And it is the correct Euler answer. The largest prime factor is 6,857. So coders, we did it. We coded the solution to the third Project Euler problem in both Scratch and in Python. We reviewed the definition of prime numbers and prime factorization, and we learned about the sieve as a algorithm to find the prime factorization of any number. I hope that you enjoyed seeing those connections between Scratch and Python. I have a kind of ongoing debate with some of the coders I know in real life who don't love Scratch. I think it's such a great language to visualize what's happening with code. For example, in that repeat until, I like how it loops all the way around your other blocks so that you understand what's happening as it repeats over and over. And then it helps me understand what's happening in Python even better. So 2 languages, 1 problem. I hope you had fun. Don't forget to like and subscribe, and we'll see you next time.